Let's start tonight with a question that's probably crossed your mind at some point, maybe while staring up at the night sky, maybe while lying awake at 3 in the morning, or maybe it just hit you out of nowhere one afternoon. The question is this: what existed before the Big Bang? It sounds like a perfectly reasonable thing to ask, doesn't it? There was this moment, roughly 13.8 billion years ago, when the universe as we know it began. Everything, every galaxy, every star, every atom in your body, the air you're breathing right now, the light from the lamp beside your bed, all of it traces back to that moment. So what was there before? What was the universe sitting inside of? What was happening in the time leading up to the biggest event in the history of, well, everything? And here's what makes this question so fascinating, and honestly, so strange. The more you learn about modern physics and cosmology, the more you start to realize that this question, what came before the Big Bang, might not actually make sense. Not because the answer is unknowable, though parts of it might be, but because the question itself might be built on an assumption that turns out to be wrong. The assumption that there was a before at all. Now, that probably sounds like a dodge, like someone trying to wriggle out of giving you a real answer. But I promise it's not. It's actually one of the deepest and most surprising things that physics has uncovered in the last century. And by the time we're done talking about it tonight, I think you'll see why. We're going to take our time with this. We'll start with the basics, what the Big Bang actually is, because it's almost certainly not what you picture when you hear the name. Then we'll trace the story of how we figured out the universe is expanding in the first place, which involves some wonderfully stubborn people and a few happy accidents. We'll talk about the nature of time itself and why Einstein's equations suggest something genuinely mind-bending about what happens when you try to rewind the clock all the way back. And then we'll explore the ideas that physicists have come up with to answer the before question, or to explain why it dissolves when you look at it closely enough. Some of those ideas are beautiful, some are wild. A few of them might keep you thinking long after you drift off tonight. So let's ease into this gently. Let's start with what most people imagine when they hear the words Big Bang. Close your eyes if they aren't already, and picture the most common version of the story. There's nothing. Absolute nothing. No space, no matter, no light. Just pure emptiness. And then, suddenly, boom, an enormous explosion. Matter and energy flying outward in all directions from a single point, like the universe's birthday firework. Everything expanding into the void, spreading out, cooling down, eventually forming galaxies and stars and planets and, billions of years later, you. It's a vivid image, and it's wrong. Or at least, it's deeply misleading in almost every way. But don't feel bad if that's what you've been picturing. It's what the name suggests, and it's the version that shows up in most popular descriptions. The name Big Bang was actually coined as an insult. The British astronomer Fred Hoyle used the term on a BBC radio broadcast in 1949 to mock the idea. He favored a competing model called the steady-state theory, which we'll get to later, and he thought the idea of the universe beginning in some kind of cosmic explosion was absurd. He called it a Big Bang sarcastically, and the name stuck. The theory Hoyle was trying to ridicule ended up being named by its biggest critic. So what actually happened, if it wasn't an explosion? Here's the first important correction. The Big Bang was not an explosion in space. It was an expansion of space itself. That distinction matters enormously, and it's worth pausing to make sure the difference really lands. When a bomb goes off, you have an explosion that happens in some pre-existing space. The debris flies outward into the room, into the air, into the empty space that was already there. The Big Bang wasn't like that. There was no pre-existing space for anything to explode into. Space itself was what was expanding. Space itself was what was being created, or stretched, or brought into being, however you want to think about it. Think about it this way. Imagine the surface of a balloon, not the inside, not the air around it, just the two-dimensional surface. Now imagine that the surface is covered with tiny dots. As you inflate the balloon, the surface stretches, and every dot moves away from every other dot. No dot is at the center of the expansion. There is no center on the surface. Every dot sees every other dot receding from it. The expansion is happening everywhere at once, and it's the fabric of the surface itself that's stretching. That's a rough analogy for what the expansion of the universe is like. Space itself is stretching, and everything in it is being carried along. Now, that analogy breaks down in some important ways. The balloon's surface is two-dimensional, while our space has 3 dimensions. And the balloon is expanding into the surrounding room, but the universe isn't expanding into anything. As far as we can tell, there is no outside. The universe might be all there is, but the key insight holds. The Big Bang was the stretching of space itself, not debris flying through pre-existing space. And if you mentally rewind that stretching, if you run the movie backward, the universe gets denser and hotter, and all the distances between things shrink. Keep rewinding, and things get unimaginably compressed. Go back far enough, and you reach a state of almost inconceivable density and temperature, where the laws of physics as we know them start to break down. That state, or something close to it, is what we mean when we talk about the Big Bang. And the numbers involved are staggering. Let me give you a sense of the scale. Right now, the observable universe is about 93 billion light-years across. That's the part of the universe we can see, the sphere of space from which light has had time to reach us since the Big Bang. Go back to 1 second after the Big Bang, just 1 second, and the entire observable universe was compressed into a region about a few light-years across, with a temperature of roughly 10 billion degrees. Go back further, to 1 microsecond after the Big Bang, and you're looking at a universe smaller than our solar system, so hot that protons and neutrons can't even hold themselves together, and everything dissolves into a seething soup of quarks and gluons. Go back to a trillionth of a second after the Big Bang, and the temperatures are so extreme that the electromagnetic force and the weak nuclear force merge into a single unified force. The entire observable universe is smaller than a planet, and the energy densities are beyond anything we can recreate in any laboratory on Earth, though the Large Hadron Collider at CERN comes closer than you might think. And here's what's wild. We can actually test some of this. The Big Bang isn't just a story. It makes specific, detailed predictions about what the universe should look like today if it really started that way. And we can check those predictions against observations. The cosmic microwave background is one. The abundance of light elements is another. The Big Bang model predicts very specific ratios of hydrogen, helium, and lithium that should have been produced in the first few minutes of the universe, and when we measure the actual abundances, they match beautifully. The large-scale structure of galaxies, the way they're distributed in space in great filaments and walls and voids, that matches too. The Big Bang isn't a creation myth. It's a scientific theory with a track record of successful predictions, tested against real data, refined over decades. And that's what gives our question its weight. When we ask, what came before the Big Bang, we're not asking about a myth. We're asking about a well-tested scientific description of the universe's history and probing the limits of what it can tell us. And here's the thing, we can actually see evidence of that early state. Right now, tonight, it's all around you. It fills every cubic centimeter of the universe. It's called the cosmic microwave background, and it's one of the most remarkable discoveries in the history of science. But we'll get to that in a little while. First, let's rewind the story even further. Not the story of the universe, but the story of how we figured all of this out. Because the path to understanding the Big Bang is itself a beautiful and surprising tale, full of wrong turns, stubborn geniuses, and moments of accidental brilliance. For most of human history, people assumed the universe was eternal and unchanging. The stars moved across the sky in their predictable patterns, the seasons cycled, and the cosmos just was. It had always been there, and it always would be. Even Isaac Newton, whose laws of motion and gravity transformed our understanding of the physical world, assumed the universe was essentially static, infinite, maybe, filled with stars, certainly, but fundamentally unchanging on the largest scales. That was the default assumption, and it persisted for centuries. It's a very human assumption when you think about it. Our lifetimes are so short compared to cosmic timescales that the universe looks frozen to us. The constellations your grandparents saw are essentially the same ones you see. So it feels natural to assume that's just how things are. Permanent, fixed, eternal. Then along came Albert Einstein, and everything changed. In 1915, Einstein published his general theory of relativity, which is, to this day, our best description of how gravity works. And what it actually describes is not a force pulling objects together, but the curvature of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells objects how to move. That's the famous summary. A star doesn't reach out and grab a planet with an invisible rope. Instead, the star's mass warps the fabric of space-time around it, and the planet follows the curved path that the warped space-time creates. If you've ever seen the demonstration with a heavy ball on a stretched rubber sheet, where a marble rolls in a curve around the dip the ball makes, it's a bit like that. A bit. The real mathematics is much richer and stranger, but the intuition is useful. Now, let's pause for a moment on what general relativity actually says, because it's genuinely one of the most beautiful ideas in the history of human thought, and it's directly relevant to everything we're going to talk about. Before Einstein, we had Newton's picture. Space is a fixed, rigid container, and gravity is a force that reaches across that container to pull objects toward each other. The Earth pulls on you, you pull on the Earth, and that mutual pull is what keeps your feet on the ground. It's a picture that works brilliantly for most purposes. It got us to the moon and back. But it has a deep problem that Newton himself acknowledged. It requires gravity to act instantly across any distance, which seems like magic. How does the sun know how far away the Earth is so it can pull with the right strength? Newton had no answer for that, and it bothered him. Einstein's answer was radical. Gravity isn't a force at all, not in the traditional sense. It's geometry. Mass and energy curve space-time, and objects moving through curved space-time follow the curves. The Earth isn't being pulled toward the sun by an invisible rope. The Earth is moving in a straight line, the straightest possible line, in the curved space-time around the sun. But because space-time is curved, that straight line happens to look like an orbit. It's a bit like how an airplane, flying the shortest path between two cities on a globe, traces a curve when you project it onto a flat map. The path is straight in the real geometry. It only looks curved because you're picturing it in a flattened version of reality. Now, here's where it gets interesting for our story. When Einstein applied his equations to the universe as a whole, when he tried to describe the shape and behavior of all of space-time, the equations didn't give him a static universe. They gave him a universe that was either expanding or contracting. The math simply didn't allow for a universe that just sat there, unchanging. Space had to be doing something. It had to be dynamic. This deeply bothered Einstein. Remember, in 1917, when he was working on this, everyone assumed the universe was static. There was no observational evidence for expansion. The idea that the universe might be growing or shrinking seemed absurd. So Einstein did something he later called his greatest blunder. He added a term to his equations, a fudge factor really, called the cosmological constant. Its sole purpose was to prop up the universe, to counterbalance gravity's tendency to pull everything together, and to keep the equations giving a static solution. He essentially put his thumb on the scale to make the math match what everyone believed the universe was doing: nothing. And then, within about a decade, the observations caught up, and Einstein's fudge factor turned out to be unnecessary. The universe wasn't static after all. It was expanding. And the person who figured this out, or at least, who provided the definitive observational proof, was an American astronomer named Edwin Hubble. But before we get to Hubble, there's someone else who deserves a moment, someone whose contribution was overlooked for decades and is only now getting proper recognition. His name was Georges Lemaitre, and he was a Belgian priest and physicist. In 1927, 2 years before Hubble published his famous observations, Lemaitre independently derived from Einstein's equations that the universe should be expanding, and he used existing astronomical data to estimate the rate of that expansion. He published his results in a French-language journal that didn't get much international attention. When Lemaitre presented his ideas to Einstein at a conference, Einstein reportedly told him, "Your calculations are correct, but your physics is abominable." Einstein wasn't ready to accept what his own equations were telling him. Lemaitre didn't stop there, though. He took the expansion and ran it backward in his mind. If the universe is expanding now, then in the past it must have been smaller, denser, hotter. Go far enough back, and everything would have been compressed into an incredibly tiny, incredibly dense state that Lemaitre called the primeval atom, a cosmic egg from which everything hatched. This was, in essence, the first version of what we now call the Big Bang Theory. And it came from a Catholic priest who was also a brilliant mathematician. There's something wonderfully human about that, the idea that a man who spent his mornings contemplating the infinite in church spent his afternoons contemplating the infinite in equations, and saw no contradiction between the two. Now, Edwin Hubble. In 1929, working at the Mount Wilson Observatory in California, at the time home to the largest telescope in the world, Hubble made the observations that changed everything. He was studying distant galaxies, and he noticed something remarkable. Almost every galaxy he observed was moving away from us. And not just moving away. The farther away a galaxy was, the faster it was receding. There was a direct relationship between distance and speed. This relationship is now called Hubble's law, and it's one of the most important discoveries in the history of science, though it probably should be called the Hubble-Lemaitre law, which is what the International Astronomical Union officially renamed it in 2018. Think about what Hubble's observation means. Every galaxy is moving away from every other galaxy. The farther apart they are, the faster they're separating. This is exactly what you'd expect if space itself is stretching, if the fabric of the universe is expanding uniformly. It's that balloon analogy again. Every dot on the surface moves away from every other dot, and dots that are farther apart move away faster because there's more expanding surface between them. And the way Hubble measured this is beautiful in its cleverness. He used something called the redshift. Light from a source that's moving away from you gets stretched to longer wavelengths, shifted toward the red end of the spectrum. It's the same physics that makes a fire truck's siren sound lower in pitch as it drives away from you. That's the Doppler effect for sound. Redshift is the Doppler effect for light. By measuring how much the light from distant galaxies was shifted toward the red, Hubble could determine how fast each galaxy was receding. And by using a particular type of pulsating star, called a Cepheid variable, whose intrinsic brightness is predictable, so you can use its apparent brightness to calculate its distance, he could determine how far away each galaxy was. Plot recession speed against distance, and you get a straight line. That line is Hubble's law, and its slope, the Hubble constant, tells you the rate at which the universe is expanding. Measuring that constant precisely has been one of the great projects of observational cosmology, and as of right now, there's actually a tension in the measurements. Different methods give slightly different values, and nobody's quite sure why. It might be a systematic error in one of the measurements, or it might be a hint of new physics. Another open question to add to the pile. This was stunning. It meant the universe had a history. It meant the universe was changing, evolving, dynamic. It meant that if you ran the clock backward, the universe would have been smaller, denser, hotter. It meant there was a beginning, or at least something that looked very much like one. And it meant Einstein's cosmological constant, his greatest blunder, had been unnecessary all along. The universe didn't need to be propped up because it wasn't standing still. Although, and here's a wonderful twist, in 1998, observations of distant supernovae revealed that the expansion of the universe isn't just continuing, it's accelerating. Something is pushing space apart faster and faster. We call it dark energy, and we have no idea what it is. And the simplest mathematical description of dark energy is, wait for it, Einstein's cosmological constant. The very thing he dismissed as his greatest blunder turned out to describe a real feature of the universe, just not in the way he intended. His mistake was ahead of its time, but not everyone was convinced. This is where one of the great scientific debates of the 20th century comes in, and it's a debate worth savoring because it shows how science actually works, how competing ideas clash, and how evidence eventually settles the argument. On one side, you had the Big Bang model, championed by Lemaitre and later refined by the Russian-American physicist George Gamow. On the other side, you had the steady-state theory, proposed in 1948 by Fred Hoyle, Thomas Gold, and Hermann Bondi. The steady-state model was elegant in its own way. It accepted that the universe was expanding. The evidence for that was, by now, overwhelming, but it proposed that new matter was continuously being created out of nothing, just enough to fill in the gaps left by the expansion. So the universe was expanding, yes, but it always looked the same on the largest scales. No beginning, no end, no special moment of creation. It was eternal, steady, and self-renewing. There's something philosophically appealing about the steady-state model, isn't there? It avoids the uncomfortable question of what came before. If the universe has always existed, there is no before. The question dissolves. And Hoyle, who was a brilliant astrophysicist in his own right, argued passionately for it. He found the idea of a universe with a definite beginning almost offensive. It felt too much like a creation myth to him, too close to theology, which is ironic, given that the man who first proposed the Big Bang model was a priest. And Hoyle, despite being wrong about the Big Bang, made enormous contributions to astrophysics in other areas. He was one of the people who figured out how stars forge heavy elements, carbon, oxygen, iron, all the elements heavier than helium, through nuclear fusion in their cores. He described how dying stars scatter these elements into space, where they become the raw materials for new stars, new planets, and eventually new life. The famous phrase, "We are stardust," is basically a summary of Hoyle's work on stellar nucleosynthesis. So here was a man who understood, better than almost anyone, how the atoms in your body were forged in stellar furnaces, and yet he couldn't accept that the universe itself had a beginning. Science is done by humans, with all their brilliance and all their stubbornness, and that's part of what makes the story worth telling. So how do you settle a debate like this? You look for evidence that would distinguish the two models. And in 1948, George Gamow and his students Ralph Alpher and Robert Herman made a prediction that turned out to be decisive. They calculated that if the universe really did start in an incredibly hot, dense state and then expanded and cooled, then the radiation from that early fireball should still be around today. It would have been stretched by the expansion of space from its original extremely high-energy form into much longer, cooler wavelengths, specifically microwaves. The entire universe should be filled with a faint glow of microwave radiation, a kind of afterglow of the Big Bang, with a temperature of just a few degrees above absolute zero. This was an extraordinary prediction, and for nearly 2 decades, nobody detected it. It just sat there in the literature, a theoretical prediction waiting for an experiment. And then, in 1964, something wonderful happened. One of those accidental discoveries that reminds you how much of science depends on paying attention to what you didn't expect. 2 radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna to detect faint radio signals bounced off satellite balloons. They were doing practical telecommunications work, not cosmology, but they kept picking up a persistent hiss of static that they couldn't eliminate. They checked everything. They recalibrated the antenna. They pointed it in every direction. The hiss was the same no matter where they pointed. It was coming from everywhere. They even climbed inside the antenna and cleaned out the pigeon droppings that had accumulated, thinking that might be the source. It wasn't. The hiss remained. Eventually, through a chain of conversations and a bit of luck, Penzias and Wilson connected with a group of physicists at nearby Princeton University, Robert Dicke, Jim Peebles, and their colleagues, who were in the process of building their own antenna to search for exactly this kind of radiation. The Princeton group had independently predicted the cosmic microwave background, not knowing about Gamow's earlier prediction. When Penzias and Wilson described their mysterious hiss, the Princeton team immediately recognized what it was. The 2 groups published back-to-back papers in 1965. Penzias and Wilson described the observation. The Princeton group explained what it meant. They had found the afterglow of the Big Bang. That faint hiss of microwaves is the oldest light in the universe, released roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for light to travel freely for the first time. Before that moment, the universe was a hot, opaque plasma, a blinding fog of particles and radiation too dense for light to pass through. Photons couldn't travel more than a short distance before slamming into a charged particle and bouncing off in another direction. The universe was like a blinding white fog, luminous and impenetrable. Then, as the temperature dropped below about 3,000 Kelvin, something remarkable happened. Electrons slowed down enough to be captured by atomic nuclei, forming the first neutral atoms, mostly hydrogen and helium. And neutral atoms are transparent to light. Suddenly, the fog lifted. The universe went from opaque to clear in what was, cosmologically speaking, a relatively brief transition. And all that trapped light was released at once, flooding outward in every direction. That light has been traveling ever since, for 13.8 billion years, stretched by the expansion of space from its original blazing visible light wavelengths. It would have looked like a warm orange glow if you'd had eyes to see it, into the cool microwaves we detect today. It fills the entire universe. It's everywhere, right now, in this room, passing through you as you lie there. About 1% of the static on an old analog television set that isn't tuned to a channel comes from this radiation. You've been watching the afterglow of creation without knowing it. And when we map this radiation in detail, which we've done with exquisite precision using satellites like COBE in 1989, WMAP in 2001, and Planck in 2009, we see that it's not perfectly uniform. There are tiny fluctuations, variations of about 1 part in 100,000, like very faint ripples in what's otherwise a perfectly smooth bath. And those ripples are incredibly important. They're the seeds of everything. Those tiny variations in density in the early universe are what eventually grew, under the pull of gravity over billions of years, into the galaxies, galaxy clusters, and vast cosmic structures we see today. The cosmic microwave background isn't just a baby photo of the universe. It's a map of the initial conditions from which everything we see around us grew. Every galaxy, every star, every planet, every person, all of it traces back to those faint ripples in the primordial light. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery. And the steady-state theory, for all its elegance, was effectively dead. The cosmic microwave background was exactly what the Big Bang model predicted, and exactly what the steady-state model couldn't explain. There was no reason for the universe to be filled with this uniform microwave glow if the universe had always existed in its current state. But there was every reason for it if the universe had once been incredibly hot and dense and had been expanding and cooling ever since. So by the late 1960s, the scientific community had largely accepted the Big Bang as the correct description of the universe's history. The universe began in an extremely hot, dense state, approximately 13.8 billion years ago, and it's been expanding and cooling ever since. The cosmic microwave background is its birth certificate, its baby photo, the oldest snapshot we have. And now, we arrive at the question that started all of this. If the universe began 13.8 billion years ago, what was there before that? What preceded the Big Bang? This is where things get genuinely strange. And to really appreciate why, we need to talk about something we usually take for granted: time. Not time as in, what time is it? But time as a fundamental feature of reality. What is it? Where does it come from? And, this is the crucial part, is it possible for time itself to have a beginning? In our everyday experience, time feels absolute. It flows forward at a constant rate, independent of everything else. A second is a second is a second, whether you're running a marathon or lying in bed. The past is behind us, the future is ahead, and time marches on, regardless of what happens in the physical world. That's the common sense picture, and it's essentially Newton's picture too. Newton described time as flowing equably, without regard to anything external. It was a backdrop, a stage on which events happened, but that wasn't affected by those events. Einstein demolished this picture. In his special theory of relativity, published in 1905, he showed that time is not absolute. It depends on how fast you're moving. A clock on a speeding spaceship ticks slower than a clock sitting on your desk. Not because the spaceship clock is broken. Time itself actually passes more slowly for objects in motion. The faster you move, the slower your time flows, relative to someone standing still. This isn't a metaphor or a thought experiment. It's been measured. Atomic clocks flown on airplanes tick slightly slower than identical clocks left on the ground. GPS satellites have to correct for this effect. Without those corrections, your navigation app would be off by kilometers within a day. But the deeper revolution came with general relativity in 1915. Here, Einstein showed that it's not just speed that affects time. Gravity does too. Time runs slower in stronger gravitational fields. A clock on the surface of the Earth ticks slightly slower than a clock in orbit. A clock near a black hole would tick dramatically slower than one far away. And this isn't just about clocks. Time itself, the actual passage of moments, is affected by gravity. Near a massive object, time literally moves more slowly. The effect is real and measurable in everyday technology. The GPS satellites orbiting the Earth are in a weaker gravitational field than clocks on the ground, so their clocks tick faster, by about 45 microseconds per day. They're also moving fast relative to the ground, which makes them tick slower by about 7 microseconds per day due to the speed effect from special relativity. The net effect is that satellite clocks gain about 38 microseconds per day compared to ground clocks. That sounds tiny, but if you didn't correct for it, GPS positions would drift by about 10 kilometers per day. Your navigation app works because Einstein was right about the nature of time. Every time you use GPS to find a restaurant or navigate to a friend's house, you're relying on the fact that time is flexible, that it runs at different rates depending on gravity and speed. You're using general relativity without knowing it. And here's the key insight for our question. In general relativity, time is not separate from space. They're woven together into a single four-dimensional fabric called space-time. You can't have one without the other. Space and time are not a stage on which the universe performs. They are part of the performance. They bend, stretch, warp, and curve in response to the matter and energy they contain. Space-time is dynamic. It's a thing, not a background. Think about what that means for the Big Bang. If space-time is part of the universe, if it's not a pre-existing backdrop but something that was born with the universe, then the question, what came before the Big Bang, runs into a profound problem. Before is a time word. It refers to an earlier moment on the timeline. But if time itself began with the Big Bang, then there is no before. Asking what came before the Big Bang is like asking what's north of the North Pole. The question uses language that seems sensible, but points to something that doesn't exist. Now, let's sit with that for a second, because it's a genuinely weird idea, and it deserves to be unpacked. We're so used to thinking of time as a river that flows endlessly in both directions, from an infinite past through the present and into an infinite future, that the idea of time having a starting point feels almost impossible to grasp. Our brains evolved to navigate a world where causes precede effects, and every event has a prior event. The question, what happened before, feels hardwired into our thinking, and now physics is telling us that this question might not apply to the universe as a whole. That's a lot to absorb. The person who articulated this most clearly was Stephen Hawking. In a famous lecture, he compared asking, what came before the Big Bang, to asking, what's south of the South Pole? You can stand at the South Pole and point south, but there's nothing more south to go. South ends there, not because there's a wall or a boundary, but because you've reached the limit of what south means. Similarly, if time began at the Big Bang, then before ends there, not because something is blocking your view, but because you've exhausted what before refers to. Hawking, together with the mathematician Roger Penrose, proved a series of theorems in the late 1960s and early 1970s, now called the Penrose-Hawking singularity theorems, that showed something unsettling. Penrose had already shown in 1965 that singularities are an inevitable feature of gravitational collapse, that a massive enough star, when it runs out of fuel, must collapse to a singularity, a point of infinite density at the heart of what we now call a black hole. Hawking took that result and turned it around. If singularities are inevitable at the end of a star's collapse, he asked, what happens when you apply the same reasoning to the universe as a whole, running backward in time? The answer was striking. If general relativity is correct, and certain reasonable conditions are met, specifically, that the universe contains enough matter and energy, which it clearly does, then the universe must have begun in a singularity. A singularity is a point where the mathematics of general relativity breaks down, where density becomes infinite, where the curvature of spacetime becomes infinite, where the equations give you answers of infinity, which in physics is another way of saying we don't actually know what happens here. At a singularity, our theory stops working. It's like a map that just ends. The territory might continue, but the map can't show it. And here's the thing. This isn't just a mathematical curiosity. The singularity theorems mean that if you run the expansion of the universe backward using general relativity, you inevitably arrive at a point of infinite density and curvature. The equations scream at you. They say, something happened here that I can't describe. This is the classic Big Bang singularity, and it's the point where most popular descriptions say, the universe began. But the more honest way to put it is, this is the point where our best theory of gravity breaks down and can no longer tell us what's happening. This is a really important distinction, so let me say it again a different way. When physicists say the universe began with the Big Bang, they're not necessarily saying that there's a moment of absolute beginning where everything popped into existence from literal nothing. What they're saying is, if we use general relativity to trace the history of the universe backward, we hit a singularity at a finite time in the past, about 13.8 billion years ago, where the theory breaks. We can describe everything from a tiny fraction of a second after that point onward, with extraordinary precision. But at the singularity itself, and anything before it, general relativity has nothing to say. The map ends. So here's the deep question. Does the singularity represent a genuine beginning of time, or does it represent a failure of our theory? Is the singularity telling us that time really started there, or is it telling us that general relativity is incomplete, and that a more fundamental theory would show us what happened at and possibly before that point? Most physicists today believe the singularity is a sign that general relativity is incomplete, not that time literally began. And the reason they believe this has to do with quantum mechanics. You see, general relativity is a theory of the very large. It describes gravity, space-time, the structure of the cosmos. Quantum mechanics is a theory of the very small. It describes atoms, particles, the behavior of matter at the tiniest scales. Both theories are spectacularly successful in their own domains. General relativity predicts the bending of light around stars, the existence of black holes, the expansion of the universe, all confirmed by observation. Quantum mechanics predicts the behavior of semiconductors, the structure of atoms, the emission of light, all confirmed with astonishing precision. But here's the problem. The two theories don't get along. They use different mathematical frameworks. They make different assumptions about the nature of reality. And when you try to combine them, when you try to apply quantum mechanics to gravity itself, the equations give you nonsense. Infinities crop up everywhere. The math falls apart. For nearly a century, physicists have been trying to develop a theory of quantum gravity, a framework that would unite general relativity and quantum mechanics into a single coherent description of nature at all scales. And as of right now, we don't have one. We have candidates: string theory, loop quantum gravity, a few others, but none of them is complete, and none has been confirmed by experiment. And this is directly relevant to the question of what existed before the Big Bang, because the Big Bang singularity is exactly the kind of situation where both gravity and quantum mechanics matter. At the very earliest moments of the universe, everything was compressed into a region so small that quantum effects would have been enormous, and so dense that gravitational effects would have been extreme. To understand what happened at or before the Big Bang, you would need a theory that handles both. You'd need quantum gravity, and we don't have it yet. So when someone asks what existed before the Big Bang, the most honest answer from physics right now is, we don't know, because we don't yet have the theory we'd need to answer that question. General relativity, our best theory of gravity, breaks down at the singularity. Quantum mechanics, our best theory of the small, doesn't include gravity. Until we have a theory that does both, the question of what happened at or before the Big Bang remains open. This is one of the great unfinished projects in physics, and it's worth appreciating just how hard it is. People have been working on quantum gravity since the 1930s, when it became clear that quantum mechanics and general relativity didn't play well together. That's almost a century of effort by some of the most brilliant minds in physics, and we still don't have a complete answer. The difficulty isn't just mathematical, though the math is ferociously hard. It's conceptual. In quantum mechanics, events happen in a fixed background of space and time. You have a particle, and you ask where it is at a given time, and quantum mechanics gives you a probability. But in general relativity, space and time are themselves dynamic. They bend and stretch and warp. So to quantize gravity, you'd need to quantize space-time itself. You'd need a quantum theory of the stage on which all other quantum theories are set. You'd need the background to be quantized while simultaneously serving as the background. It's a conceptual hall of mirrors, and nobody has found a clean way through it yet. The Planck scale, roughly 10 to the minus 35 meters, 10 to the minus 43 seconds, and 10 to the minus 8 kilograms, marks the boundary where quantum gravitational effects should become dominant. These numbers are derived from combining the fundamental constants of nature, the speed of light, Newton's gravitational constant, and Planck's constant. At the Planck length, the quantum fuzziness of spacetime should be as large as the spacetime itself. Distances shorter than the Planck length might not even make sense. Time intervals shorter than the Planck time might not be meaningful. And the energy density at the Planck scale is so enormous that gravity and quantum mechanics are forced to coexist, and we'd need a unified theory to describe what happens. The Big Bang singularity sits right at this scale. To understand it, we need to understand the Planck scale. To understand the Planck scale, we need quantum gravity. And we're not there yet, but that doesn't mean physicists haven't tried to answer it. They've come up with some extraordinary ideas. Speculative, yes, but grounded in real physics and real mathematics. And these ideas are genuinely fascinating, even if none of them is confirmed. So let's explore a few of them. Let's see what some of the best minds in physics think might have existed before the Big Bang, or why the question itself might dissolve once we understand things better. Let's start with one of the most elegant proposals, one that Hawking himself developed with the physicist James Hartle. It's called the no-boundary proposal, or sometimes the Hartle-Hawking state, and it was first put forward in 1983. Here's the basic idea. In quantum mechanics, particles don't have definite trajectories. They exist in a kind of probabilistic haze until they're observed. Hawking and Hartle tried to apply this quantum fuzziness to the universe as a whole, including to the moment of its birth. They used a mathematical technique called a Wick rotation, where you replace ordinary time with what's called imaginary time, time measured not in real numbers, but in a specific kind of imaginary number. Now, imaginary time sounds like science fiction, but it's a well-established mathematical tool in quantum physics. And when you use imaginary time, something remarkable happens to the Big Bang singularity. It smooths out. Instead of a sharp point where everything begins, you get a rounded surface, like the bottom of a bowl or the south pole of a sphere. And on a sphere, there's no edge, no boundary. The South Pole isn't a beginning or an end. It's just another point on the surface. In the Hartle-Hawking picture, the universe has no boundary in time. Time doesn't begin at a singularity. It simply rounds off, smoothly, into a configuration where the question, what came before, has no meaning, because there is no before. Time, in this picture, is finite but unbounded, just like the surface of the Earth is finite but has no edge you could fall off. This is beautiful and strange and incredibly hard to wrap your mind around, but that's the idea. The universe didn't pop into existence from nothing. It didn't emerge from something that was there before. It's self-contained. It has no boundary, no edge, no starting point. It just is. Hawking put it memorably when he asked, "What place, then, for a creator?" Not as an argument against God, necessarily, but as a way of showing that the universe might not need an external cause. It might be its own explanation. Now, there are problems with the no-boundary proposal. The mathematics is fiendishly difficult, and different ways of doing the calculation give different answers. Some physicists have argued that the Hartle-Hawking state, when calculated properly, actually predicts a universe that looks nothing like ours, one that's empty rather than filled with matter and radiation. The debate is ongoing and highly technical. But as a conceptual framework, as a way of thinking about what before means when you apply quantum mechanics to cosmology, it remains one of the most influential ideas in the field. And it's worth noting that this idea, the no-boundary proposal, is a genuine attempt to do quantum cosmology. It treats the entire universe as a quantum system and asks, what is the wave function of the universe? Just as a single electron has a wave function that tells you the probability of finding it in various places, the universe as a whole might have a wave function that tells you the probability of it having various shapes and sizes and histories. The Hartle-Hawking wave function is one proposal for what that universal wave function looks like. It's audacious. It's the application of quantum mechanics, not to a particle or an atom, but to everything, all of space-time, all at once. Whether it's right or wrong, the sheer ambition of the question is breathtaking. We're talking about calculating the quantum probability for the existence of everything. And this connects to an even deeper issue, the problem of quantum cosmology itself. In ordinary quantum mechanics, there's always an observer outside the system being studied. You measure the electron's position. You observe the photon's spin. But in quantum cosmology, there is no outside. You're trying to apply quantum mechanics to the universe, and you're inside the universe. There's no external observer, no apparatus, no laboratory. Just the universe, doing its quantum thing, with us inside it trying to figure out the rules. This makes quantum cosmology conceptually murky in ways that ordinary quantum mechanics isn't, and different physicists have very different opinions about whether it even makes sense. But the question won't go away, because the Big Bang itself was a quantum gravitational event. And to understand it, we need some form of quantum cosmology, however strange it might be. Let's talk about another idea, one that approaches the question from a completely different angle: inflationary cosmology. This is one of the most important ideas in modern physics, and it was first proposed by a young physicist named Alan Guth in 1980. To understand inflation, you need to know about a puzzle. Actually, several puzzles. And the story of how Guth came up with inflation is one of those great tales of scientific insight that's worth telling properly. Guth was a young postdoctoral researcher at the Stanford Linear Accelerator Center in 1979, working on problems in particle physics, not cosmology. He attended a lecture by Robert Dicke about the puzzles plaguing the Big Bang model, and something clicked. He went home and started scribbling in his notebook. On December 12, 1979, the date is recorded in his actual notebook, which is now a kind of artifact in the history of physics. He wrote in capital letters across the top of a page, "Spectacular realization." He'd found a mechanism that could solve the puzzles all at once. By the late 1970s, the Big Bang model was well established, but it had some nagging problems. The most famous is called the horizon problem. Here's what it is. When we look at the cosmic microwave background, that ancient afterglow we talked about, we see that it has almost exactly the same temperature everywhere. Every direction you look, the temperature is about 2.725 Kelvin. The variations are tiny, 1 part in 100,000. The universe's baby photo is remarkably uniform, but here's the problem. Different parts of the sky that we see today were, at the time the microwave background was released, so far apart that they could never have been in contact with each other. Light, even traveling since the Big Bang, hadn't had enough time to get from one region to the other. They were beyond each other's horizons. So how did they end up at the same temperature? It's like finding out that two people on opposite sides of the planet who've never communicated are wearing the exact same outfit down to the socks. How did they coordinate? In everyday physics, if you want two things to reach the same temperature, you put them in contact. You let heat flow between them until they equilibrate. But these regions of the early universe were never in contact. So how did they equilibrate? Alan Guth's answer was inflation. He proposed that in the first tiny fraction of a second after the Big Bang, we're talking about something like 10 to the minus 36 seconds, an almost inconceivably brief instant, the universe underwent a period of extraordinarily rapid expansion. Not the gradual expansion we see today, but an exponential, mind-boggling inflation, where the universe doubled in size over and over again in an incredibly short time. In a fraction of a second, a region smaller than an atom was stretched to something larger than the observable universe we see today. And this solves the horizon problem beautifully. Before inflation, the entire observable universe was contained in a tiny region, small enough that everything in it was in causal contact. Everything could communicate with everything else, and temperatures could equilibrate. Then inflation stretched that tiny, uniform region to enormous size, carrying its uniformity with it. The microwave background is uniform because the universe started small enough to be uniform and then was blown up like a balloon. Inflation also solves another puzzle called the flatness problem. The geometry of the universe, whether space is curved like a sphere, saddle-shaped or flat, depends on a balance between the energy content of the universe and its expansion rate. If the universe were even slightly curved at the time of the Big Bang, that curvature would have been amplified enormously by the subsequent expansion. For the universe to appear as flat as it does today, and observations show it's very, very close to flat, the balance at the Big Bang would have had to be perfect to an astonishing degree. Something like 1 part in 10 to the 60th. That kind of fine-tuning seems unnatural. Inflation explains it by taking whatever initial curvature the universe had and stretching it so much that any curvature was diluted to essentially zero, just as inflating a balloon enough makes any small patch of its surface look flat. But inflation does something else that's even more remarkable, and this connects back to those tiny ripples in the cosmic microwave background. During inflation, the universe was expanding so violently that quantum fluctuations, the tiny, random variations in energy that quantum mechanics says are always present in any field, were stretched from subatomic scales to cosmic scales. These quantum fluctuations, normally confined to the realm of the incredibly small, were inflated to sizes spanning the observable universe. And those stretched-out quantum fluctuations became the seeds of all the structure we see in the universe today. The galaxies, the galaxy clusters, the great cosmic web of filaments and voids, all of it grew from quantum noise, amplified by inflation. Think about that for a second. The largest structures in the universe, structures spanning hundreds of millions of light years, trace their origin to random quantum jitters in a field that existed for less than a trillionth of a trillionth of a trillionth of a second. The very small dictated the shape of the very large. That's one of those connections across scales that takes your breath away when you really absorb it. And we can test this. Inflation makes specific predictions about the statistical properties of those ripples in the microwave background, their spectrum, their distribution, their correlations, and when we measure them, with satellites like Planck, the predictions match. The agreement is remarkable. It's one of the strongest pieces of evidence that inflation actually happened, though it's worth saying that inflation isn't proven beyond doubt. There are alternative models that can also explain the data, and inflation itself comes in many versions with different details. The basic idea, a period of extremely rapid expansion in the early universe, is widely accepted, but the specifics are still being worked out. But here's where inflation leads us somewhere unexpected, somewhere that connects directly to our question about what came before the Big Bang. You see, in most versions of inflation, the rapid expansion is driven by a hypothetical field called the inflaton field, which is in a high-energy state that acts like a kind of repulsive gravity, pushing space apart at an accelerating rate. Eventually, the inflaton field decays to a lower energy state, releasing its energy as a flood of particles and radiation. This is the reheating that marks the end of inflation and the beginning of what we'd recognize as the hot, particle-filled universe. The Big Bang, in this picture, is not the very beginning of everything. It's the end of inflation. It's the moment when inflation stopped and the familiar expansion began. And here's where it gets really interesting. In many versions of inflation, particularly a variant called eternal inflation, developed by physicists like Andrei Linde, Alexander Vilenkin, and Alan Guth himself, inflation doesn't stop everywhere at once. It stops in our region of space, which becomes our universe. But in other regions, inflation keeps going. And in those still inflating regions, new bubbles of non-inflating space keep forming, each one becoming its own universe with its own Big Bang, its own physical constants, possibly its own laws of physics. The inflationary process goes on forever, endlessly spawning new universes in an ever-expanding foam of space-time. This is one version of the multiverse. In this picture, our Big Bang is not the beginning of everything. It's a local event, the formation of one bubble in an endlessly inflating background. There was something before our Big Bang, the inflating space-time from which our bubble universe nucleated. And that inflating space-time may have always existed, or it may have had its own beginning, which leads to further questions. Vilenkin, for instance, has proposed that the inflating space-time itself could have emerged from a quantum tunneling event, literally popping into existence out of nothing, not nothing as in empty space, but nothing as in no space, no time, no laws, no anything. A quantum fluctuation in genuine nothingness that brought space-time into being. Now, you might be thinking, that sounds like it doesn't actually answer the question, it just pushes it back a step. And you'd be right to some degree. If inflation came before the Big Bang, what came before inflation? If a quantum tunneling event created the inflating space-time, what made that tunneling possible? These are real and serious questions, and physicists wrestle with them. The honest answer is that we don't know how far back the chain goes, or whether the chain even has a first link. But inflation has shifted the question. It's shown that the Big Bang, as dramatic as it is, might not be the absolute beginning. It might be just one event in a much larger and older story. And there's something else about eternal inflation that's worth sitting with, because it's genuinely disorienting. If our universe is one bubble in an infinitely inflating space-time, then there are other bubbles, other universes, and they might have different physical constants, different particle physics, different laws. In some, gravity might be stronger. In some, electrons might be heavier. In some, the conditions might never allow stars to form at all. This is one version of the multiverse, and while it's speculative, it's not arbitrary speculation. It follows from well-motivated physics, and it might be testable. If our bubble universe collided with a neighboring bubble at some point in the past, the collision would leave a circular bruise in the cosmic microwave background. Physicists have searched for these bruises. So far, nothing definitive, but the search continues. Imagine that, looking at the oldest light in the universe and asking whether it carries the fingerprint of another universe bumping into ours. That's where we are. That's the frontier. Let's shift gears and talk about another approach, one that comes from the attempt to build that theory of quantum gravity we mentioned earlier. One of the most developed candidates is called loop quantum gravity. It was pioneered by physicists like Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, and it takes a radically different approach to space-time than the one we're used to. In loop quantum gravity, space is not smooth and continuous. At the very smallest scales, the Planck scale, roughly 10 to the minus 35 meters, a distance so small that it makes an atom look like a galaxy, space is made up of discrete, granular units. Think of it as though, if you could zoom in far enough, you'd find that space has a kind of weave, a fabric made of tiny loops and nodes. It's quantized, like energy levels in an atom. There's a smallest possible volume, a smallest possible area, and you can't divide space into pieces smaller than these fundamental units. And here's what that means for the Big Bang. If space is granular, if there's a smallest possible volume, then you can't compress the universe all the way down to a singularity of zero size and infinite density. The granular structure of space acts like a floor. When you run the universe backward and it gets smaller and denser, it hits this quantum floor and bounces. The singularity is replaced by a bounce, a moment of maximum compression followed by expansion. This is sometimes called the Big Bounce. In the Big Bounce picture, our universe didn't emerge from a singularity. It emerged from the collapse and re-expansion of a previous universe. Before our Big Bang, there was a contracting universe that got denser and denser until it hit the quantum gravity floor and bounced outward, expanding again to become the universe we live in. There was something before the Big Bang, another universe. And before that universe, perhaps another contraction and bounce, and before that, another, and so on, in an infinite cycle of expansion, contraction, and rebirth. There's something almost comforting about this picture, isn't there? No beginning, no end, just an eternal heartbeat. Expansion, contraction, expansion, contraction. The universe breathing in and out forever. And the mathematics of loop quantum cosmology makes specific predictions about what the bounce would look like. The density at the bounce point would be about 80% of the Planck density, roughly 5 times 10 to the 96 kilograms per cubic meter, a number so absurdly large that it defies any attempt at analogy. At that density, quantum gravitational effects dominate. The classical notion of space-time breaks down entirely, and gravity itself becomes repulsive, pushing everything apart and driving the expansion. It's not that something external causes the bounce. The bounce is built into the quantum geometry of space itself. And here's a fascinating detail. In some calculations from loop quantum cosmology, information from the previous universe can survive the bounce. Not perfectly, not completely, but there might be echoes, faint signatures of the universe that existed before ours, encoded in the cosmic microwave background, or in the large-scale structure of the universe we see today. Physicists have looked for these signatures, and the results so far are inconclusive. We haven't found a definitive signal from a previous universe, but we also can't rule it out. The idea that our universe might carry scars from a life it lived before, like a palimpsest, where the old text shows through beneath the new. That's one of those ideas that's almost too poetic to be physics, except that it is physics, with real equations and real predictions. This is an old idea, actually. The notion of a cyclic or oscillating universe goes back decades. But earlier versions ran into serious problems. Each cycle would produce more and more entropy, more disorder, and the cycles would get longer and longer. Run the clock backward, and the cycles get shorter and shorter, and you still end up with a beginning. Loop quantum gravity offers a way around some of these problems by providing a specific mechanism for the bounce, and by showing how quantum effects at the Planck scale could smooth out the singularity. There are other cyclic models too. One of the most interesting was proposed by Paul Steinhardt and Neil Turok, building on ideas from string theory. In their model, our universe is a 3-dimensional membrane, a brain, floating in a higher dimensional space called the bulk. Think of 2 sheets of paper hanging parallel to each other in a room. Each sheet is a universe, and the room is the higher dimensional bulk. Periodically, the sheets ripple and touch, and the energy of the collision drives a new Big Bang on each sheet. The 2 brains then separate, each expanding and cooling. Eventually, they're drawn back together for another collision, another Big Bang, another cycle. In this picture, the Big Bang is not a unique event, but a recurring one, a cosmic heartbeat, and each cycle can last trillions of years. So we're currently living in the expansion phase of our particular cycle, with the next collision unimaginably far in the future. It's a beautiful model, though it requires the extra dimensions predicted by string theory, which haven't been observed. String theory itself remains unconfirmed, and so the ekpyrotic model, as it's sometimes called, named after the ancient Stoic concept of universal conflagration, is speculative. But it shows how seriously physicists take the possibility that our Big Bang isn't the beginning of everything, but one chapter in an ongoing cosmic story. And then there's Roger Penrose's conformal cyclic cosmology, which is one of my favorites because it's so unexpected, and because Penrose himself is such a remarkable figure. He's now in his 90s, a Nobel laureate, a mathematician of extraordinary depth and creativity, and he's been thinking about the foundations of physics for longer than most working physicists have been alive. His cyclic cosmology proposal, which he calls CCC, is typically Penrose, elegant, mathematically sophisticated, and not afraid to be strange. Penrose proposes that the universe goes through infinite cycles, which he calls aeons. Each aeon begins with a Big Bang and ends when the universe has expanded so much, and all the matter has decayed and radiated away, that what's left is a thin soup of photons and gravitational radiation. In that extremely distant future, we're talking timescales that make the current age of the universe look like a blip. When all particles with mass have decayed, the universe becomes conformally invariant. That's a technical term that means, in essence, that the distinction between very large and very small loses meaning. When everything is massless, the concept of distance becomes ambiguous. A photon, traveling at the speed of light, doesn't experience the passage of time. In a universe made entirely of massless particles, the vastness of space and the tininess of a point become, in a precise mathematical sense, indistinguishable. Penrose argues that this extremely cold, empty, expanded state is mathematically equivalent to the extremely hot, dense, compressed state of a Big Bang. The end of one aeon is the beginning of the next. The universe doesn't bounce, it transitions. What looks like a Big Bang from one side looks like an infinitely remote future from the other. And here's where it gets really interesting. Penrose has claimed to find evidence for this in the actual data. He's identified what he calls Hawking points in the cosmic microwave background, concentric circles of slightly unusual temperature, which he interprets as the signatures of supermassive black holes from a previous aeon, their Hawking radiation leaking through the transition from one aeon to the next. Most cosmologists are skeptical of this claim, arguing that similar patterns could arise from statistical noise. The debate is unresolved. But the fact that it's even a debate, that someone is looking at real data in the cosmic microwave background and asking whether it contains messages from a previous universe, gives you a sense of how far we've come and how seriously these ideas are being taken. If your head is spinning a little, that's completely fine. These are ideas that stretch the limits of what human language and intuition can handle. The point isn't to memorize the details, it's to appreciate the range and creativity of the answers that physicists have proposed. Some say time began with the Big Bang, and there is no before. Some say inflation came before, driven by a quantum field in a high-energy state. Some say our universe bounced from a collapsing predecessor. Some say we're one bubble in an eternal foam of inflating space-time. Some say the universe cycles endlessly, with each death giving birth to a new beginning. And some say the question itself is built on a misunderstanding of what time is. Let's go deeper into that last idea, because I think it's the most philosophically profound. The notion that the question, what came before the Big Bang, might be meaningless isn't an evasion, it's a consequence of taking general relativity seriously. In Einstein's framework, time is not a stage on which the universe performs, it's part of the performance. Time is a feature of the universe, not a container for it. If the universe has a finite age, if space-time has a starting configuration, then there is no time before that configuration, because time is part of what that configuration defines. Here's an analogy that might help. Think about the number line. The natural numbers start at 1, then 2, 3, 4, and so on forever. Now ask, what natural number comes before 1? The answer isn't 0. 0 isn't a natural number in the traditional definition. The answer is that there is no natural number before 1. 1 is the beginning. There's nothing missing. The question, what comes before 1, is perfectly grammatical, but it points to something that doesn't exist within the system. Similarly, if time began at the Big Bang, asking what was before is grammatically fine, but physically empty. You've stepped outside the boundaries of what the system contains. Now you might object, and plenty of people do, that this feels like a trick. Surely something must have caused the Big Bang. Surely things don't just begin to exist for no reason. And this objection is deeply rooted in our everyday experience, where every event has a cause, and that cause precedes the event in time. But that principle, every event has a prior cause, assumes that time extends infinitely into the past. If it doesn't, the principle might not apply. Causation, as we understand it, might be a feature that emerges with time, not something that precedes it. Think about it this way. Temperature is a property of collections of particles. A single particle doesn't have a temperature. Temperature emerges when you have enough particles bouncing around that you can meaningfully talk about their average energy. In a similar way, some physicists argue that time as we experience it, the smooth, flowing progression from past to future, might be an emergent property. It might arise from the collective behavior of more fundamental quantum gravitational processes that don't themselves involve time in any familiar sense. Before the Big Bang, there might not have been time in the way we understand it, not because time was frozen or waiting to start, but because time simply wasn't a meaningful concept in whatever preceded or underlies the Big Bang. This idea that time is emergent shows up in several approaches to quantum gravity. In loop quantum gravity, the fundamental description of spacetime at the Planck scale doesn't involve time at all. The equations are timeless. They describe relationships between quantum states of geometry without reference to a flowing temporal parameter. Time, in this picture, is something that appears only at larger scales when you zoom out from the Planck scale quantum geometry and see something that looks smooth and continuous. It's like how the smooth surface of a table emerges from the rough chaos of atoms. The smoothness is real, but it's not fundamental. Similarly, the flow of time might be real. We certainly experience it, but it might not be fundamental. It might be an approximation that works beautifully at our scale, but breaks down at the Planck scale, at the Big Bang, at the places where our question, what came before, runs aground. There's a deep mystery here that's worth appreciating, even if we can't resolve it tonight. You experience time right now. As you lie there, you feel the seconds passing. You sense the progression from one thought to the next. That experience is vivid, immediate, and seemingly undeniable. And yet, some of our best physical theories suggest that at the most fundamental level, time might not exist. The experience of time's flow might be something that emerges from a deeper, timeless reality, the way wetness emerges from water molecules that aren't individually wet, or the way consciousness might emerge from neurons that aren't individually conscious. We don't know yet. But if it's true, if time is emergent, then the question, what came before the Big Bang, isn't just unanswerable, it's built on a category error. It assumes that time is fundamental and extends infinitely into the past, when in reality, time might be a feature that switches on, like a light, once the universe reaches a certain level of complexity. Before that level, the word before doesn't apply. Not because something is blocking our view, but because there's nothing for before to refer to. The terrain where before lives simply doesn't extend that far back. Let me tell you about one more idea, because it brings us to the very edge of what physics can currently say, and it has a beautiful strangeness to it. It comes from Alexander Vilenkin, a physicist at Tufts University, and it's the idea of creation from nothing. In quantum mechanics, particles can tunnel through barriers that, classically, they shouldn't be able to cross. An electron approaching a wall that's too high for it to climb can sometimes appear on the other side. It doesn't go over the wall or through the wall. It just appears beyond it, as if the wall weren't there. This is called quantum tunneling, and it's not a theoretical curiosity. It's the basis of how scanning tunneling microscopes work, how some nuclear reactions happen in stars, and how the flash memory in your phone stores data. Vilenkin proposed that the entire universe might have quantum tunneled into existence from nothing, not from empty space, not from a pre-existing vacuum, but from nothing. No space, no time, no matter, no energy, no laws of physics. Genuine nothing, the ultimate blank slate. And from that nothing, a tiny, closed universe popped into existence through a quantum tunneling event, found itself in a high-energy inflaton field, and immediately began inflating, expanding into the universe we see today. This sounds wild, and it is, but it's built on the same quantum mechanics that makes your smartphone work. The mathematics is real. Vilenkin wrote down a wave function of the universe that describes this tunneling, and the calculation gives finite, well-defined answers. The question is whether you can extend quantum mechanics to the universe itself, and whether nothing is a meaningful physical concept from which something can emerge. And here's the philosophical twist. If the universe genuinely emerged from nothing, no space, no time, no prior anything, then there truly is no before. Not because time began at some particular moment, but because there was nothing for time to be a feature of. The question, what came before the Big Bang, becomes, what came before there was a before, which is, when you think about it carefully, not really a question at all. It's a sentence that looks like a question, but doesn't refer to anything. Now, not everyone is comfortable with this. Lawrence Krauss wrote a book called A Universe from Nothing that explored these ideas, and it was criticized by philosophers, most notably David Albert, for using nothing in a way that wasn't really nothing. Krauss's nothing was the quantum vacuum, which isn't nothing at all. It's a state of a quantum field, buzzing with energy and virtual particles, governed by the laws of physics. That's something. Vilenkin's nothing is more radical. He really does mean no space, no time, no laws. But then you can ask, how can quantum mechanics operate in a state where there are no laws for it to follow? The answer isn't clear, and the debate continues. These are the kinds of questions that sit right at the boundary between physics and philosophy. And that's okay. It's actually one of the things I find most exciting about this particular topic. We're asking a question, what existed before the Big Bang, that starts in physics and ends up brushing against the deepest philosophical puzzles about existence, causation, time, and nothingness. Physics can take us a long way toward an answer, but at some point, the question becomes one that even a perfect theory might not be able to settle, because it depends on what we mean by words like before, nothing, existence, and cause, words that seem clear in everyday life, but become slippery when you push them to extremes. And you know, the ancient philosophers wrestled with these same questions, even without modern physics. Augustine of Hippo, writing in the 4th century, was asked what God was doing before he created the world. His answer was surprisingly modern. He said that time was created along with the world, so the question of what God was doing before creation was meaningless, because there was no before. He understood, at least intuitively, that time and the universe might be a package deal. And the ancient Greeks debated endlessly about whether the cosmos had a beginning. Aristotle argued it was eternal, while the atomists, like Leucippus and Democritus, imagined atoms moving through an infinite void, colliding and forming worlds over and over in an endless cycle. The question, what came before, has haunted human thought for thousands of years. What's new is that we now have actual physics, real mathematics, real observations, real experiments to bring to bear on it. We've moved the question from pure philosophy to testable science, at least partly. And that's one of the great achievements of the last century. Let me tell you about one more thread, because it connects beautifully to everything we've discussed. It's the arrow of time. You've probably noticed that time seems to have a direction. The past is different from the future. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously reheat. We remember yesterday but not tomorrow. This asymmetry, this one-way flow from past to future, is called the arrow of time, and it's deeply connected to the Big Bang. The fundamental laws of physics are almost entirely time-symmetric. If you film a collision between two billiard balls and then play the film backward, both the forward and backward versions obey Newton's laws. There's nothing in the laws themselves that says which direction time should flow. The equations work just as well in reverse. So where does the arrow come from? Why does time seem to move in one direction? The answer, as far as we understand it, is entropy. Entropy is a measure of disorder, or, more precisely, the number of ways the microscopic components of a system can be arranged while still looking the same on a macroscopic level. A neatly stacked deck of cards has low entropy. There are very few arrangements that look neatly stacked. A shuffled deck has high entropy. There are astronomically many arrangements that look shuffled. The second law of thermodynamics says that entropy tends to increase over time. Things get more disordered, not less. That's why eggs break and don't unbreak. The broken state has higher entropy, and the universe overwhelmingly tends toward higher entropy states. Think about it with a concrete example. Imagine you have a box divided in half by a partition, with all the air molecules on one side and a vacuum on the other. Remove the partition, and the gas expands to fill the whole box. You've never seen the reverse happen. You've never seen all the air molecules in a room spontaneously move to one half and leave the other half empty. It's not that it's physically impossible. The laws of physics allow it. It's that it's overwhelmingly, astronomically, cosmically unlikely. The number of ways the molecules can be spread throughout the whole box is so vastly greater than the number of ways they can all be on one side, that the odds of the spontaneous compression happening are essentially zero. Not zero, technically, but a number with so many zeros after the decimal point that the age of the universe wouldn't be enough time to wait for it. But here's the thing. The second law doesn't explain why entropy increases. It tells you that it does, but the real question is, why was entropy low in the past? If the universe were in a high entropy state, with everything already shuffled and disordered, there would be no arrow of time. Nothing would change in any preferred direction. The fact that time has an arrow, that the past is different from the future, means that the universe started in a state of remarkably low entropy. The Big Bang was an astonishingly ordered state. All that energy, all that matter, packed into an incredibly uniform, incredibly compressed configuration. And everything since then has been entropy increasing, disorder growing, the universe gradually shuffling from its improbably ordered beginning toward a more and more disordered future. So the arrow of time, the fact that you experience time as moving from past to future, is ultimately a consequence of the Big Bang. The Big Bang set the initial conditions. It provided the low entropy starting point from which entropy could increase. And that increasing entropy is what gives time its direction. Without the Big Bang, without that special initial state, there would be no arrow. There might not even be any meaningful sense in which time flows at all. And this raises yet another version of our question. Why was the Big Bang such a low entropy state? Why did the universe start so ordered? This is sometimes called the past hypothesis, the assumption that the universe began in a low entropy configuration, and it's one of the deepest open questions in physics. Roger Penrose has argued that the probability of the universe starting in such a low entropy state is staggeringly, absurdly low. He estimates something like 1 in 10 to the power of 10 to the power of 123. A number so large that writing it out in standard notation would require more digits than there are particles in the observable universe. If the initial conditions of the universe were chosen at random, the odds of getting something like our universe are essentially zero. So something selected those initial conditions. Something explains why the universe began in that particular, exquisitely ordered state. And whatever that something is, it's intimately connected to the question of what came before, or what underlies, the Big Bang. Whether it's the Hartle-Hawking no-boundary proposal smoothing out the initial conditions, or eternal inflation selecting for certain kinds of universes, or some other mechanism we haven't thought of yet, the low entropy of the Big Bang is a clue. It's telling us something about the origin of the universe that we don't yet fully understand, and it connects every aspect of your daily experience. The fact that ice melts in your drink, that memories fade, that you age, that candles burn down and never burn up, to the conditions at the very beginning of the universe. The arrow of time that you feel right now, lying in bed, feeling the minutes pass, sensing this day becoming yesterday, that arrow was set at the Big Bang. The initial conditions of the universe are the reason you experience time at all. Let's pause here and take stock, because we've covered a lot of ground tonight, and it might be nice to feel the shape of where we've been. We started with a simple question: what existed before the Big Bang? And the first thing we discovered is that the Big Bang itself isn't what most people think. It's not an explosion in space, but an expansion of space itself. We traced the story of how we figured that out, from Einstein's equations, to Lemaitre's primeval atom, to Hubble's observations, to the cosmic microwave background. We saw how the Big Bang model won out over the steady-state theory because of the evidence. That faint hiss of microwaves filling the universe, the baby photo of creation. Then we went deeper. We talked about what time really is in Einstein's framework, not a fixed backdrop, but a dynamic part of space-time, woven into the fabric of the universe. And we saw that if time is part of the universe, then the question, what came before the beginning, might not refer to anything. We explored the singularity at the Big Bang, and saw that it's probably not a real physical event, but a sign that general relativity breaks down, and a quantum theory of gravity is needed. We looked at Hawking and Hartle's no-boundary proposal, where the universe has no edge in time, no starting point, just a smooth rounding off. We talked about inflation, and how it pushes the question back. The Big Bang might not be the ultimate beginning, but the end of a period of rapid expansion. We explored eternal inflation, and the possibility that our universe is one bubble in an endless foam. We visited the big bounce of loop quantum gravity, the cyclic collisions of brane cosmology, Penrose's conformal cycles, and Vilenkin's tunneling from nothing. And underneath all of these specific proposals, we found a deeper theme. The question, what came before the Big Bang, might dissolve once we understand the nature of time at a fundamental level. Time might be emergent, arising from more basic processes that don't themselves have a temporal character. If that's the case, asking what came before the Big Bang is like asking what color a number is. It's applying a concept in a domain where it doesn't belong. So where does that leave us? What's the answer? Well, I think the honest answer is, we don't know yet. And the fact that we don't know is itself one of the most exciting things about modern physics. We're living in a time when the biggest questions about the universe, how it began, why it exists, what came before it, whether before even means anything, are still open. They're not settled. They're active areas of research. Right now, somewhere in the world, a physicist is working on a new approach to quantum gravity, a new calculation in loop quantum cosmology, a new way of thinking about the initial conditions of the universe. And any one of those efforts might crack the puzzle open, or it might take a completely new idea that nobody has thought of yet. What I find remarkable, lying here and thinking about all of this, is how far we've come. 100 years ago, we didn't even know the universe was expanding. 50 years ago, we were still debating whether the Big Bang was real. Today, we can measure the temperature of the cosmic microwave background to 1 part in 100,000. We can trace the history of the universe back to a fraction of a second after the Big Bang, and we have at least half a dozen serious, mathematically rigorous proposals for what might have come before. We've gone from "the universe has always been here" to "the universe has a definite age and history" to "the very concept of before might not apply to the universe's origin" in the span of a single century. That's astonishing. And think about what we've learned along the way. We've learned that time is not what we thought it was. It's not a river flowing at a constant rate, carrying us along. It's flexible, bendable, dependent on speed and gravity, woven into the fabric of space, and possibly emergent from something deeper. We've learned that space is not a fixed stage. It's dynamic, expanding, possibly granular at the tiniest scales, and it might have more dimensions than the 3 we experience. We've learned that the laws of physics as we understand them break down at the most extreme conditions, at the singularity, at the Planck scale, at the very beginning, and that a deeper theory is waiting to be discovered. And the question we started with, what existed before the Big Bang, turns out to be a key to all of these deeper mysteries. It's not just a question about the past. It's a question about the nature of time, the nature of space, the nature of existence itself. It asks, is the universe everything, or is it part of something larger? Is time fundamental or emergent? Is nothing a coherent concept, or is there always something? These are questions that physics is actively engaging with, and the answers, when they come, will reshape our understanding of reality as profoundly as Einstein and Hubble reshaped our understanding of the cosmos. You know, there's something deeply comforting about not knowing. I know that sounds strange, but stay with me. We live in a universe where the biggest questions are still unanswered, where the most fundamental aspects of reality, time, space, existence, are still being figured out. And that means the universe still has surprises in store for us. There are discoveries waiting to be made, insights waiting to emerge, moments of, "Oh, that's what was happening all along," that haven't happened yet. The cosmos still has secrets, and that's not a reason for frustration. It's a reason for wonder. Think about the chain of people who got us here. Einstein, who saw that space and time are woven together, and that gravity is geometry. Lemaitre, who dared to imagine the universe expanding from a cosmic egg. Hubble, who looked through a telescope and saw the galaxies fleeing. Gamow, Alpher, and Herman, who predicted the afterglow of creation. Penzias and Wilson, who found it by accident while cleaning pigeon droppings off an antenna. Hawking and Penrose, who proved the singularity theorems and then spent their careers trying to move beyond them. Guth, who dreamed up inflation in a flash of insight. Vilenkin, who imagined the universe tunneling into existence from nothing. Ashtekar, Smolin, and Rovelli, who reimagined space as something woven from quantum loops. Each of them built on the work of those who came before. Each of them saw a little further, and each of them left questions for the next generation. That's what science is, when you step back and look at it. It's a conversation across generations, a relay race where each runner carries the baton a little further and then passes it on. And the question we've been exploring tonight, what existed before the Big Bang, is one of the batons currently being carried. Somebody, somewhere, is carrying it right now. And someday, maybe in 10 years, maybe in 100, someone will set it down in a place that changes everything we thought we knew. And here's something I find deeply moving about this particular question. Unlike many questions in science which can feel remote or technical, this one is personal. Not because it affects your daily life. It doesn't, at least not in any practical sense, but because it's the question of where you come from. Not you specifically, but everything. The matter in your body, the light in your eyes, the thoughts in your mind, the space-time that cradles it all. Where did it come from? How did any of this get here? The question, what existed before the Big Bang, is really just the most precise and scientifically rigorous version of a question that every child asks and that no adult ever fully stops wondering about. Why is there something rather than nothing? The philosopher Leibniz called that the ultimate question, and maybe he was right. Physics has taken us further toward an answer than Leibniz could have imagined. We know the age of the universe. We know its temperature 1 second after the Big Bang. We know the ratio of hydrogen to helium forged in those first few minutes. We can see the afterglow of creation. We can trace the genealogy of atoms from primordial nucleosynthesis through stellar furnaces to the molecules in your bloodstream. But the deepest layer, why there's a universe at all, and whether it emerged from something or nothing, or a previous universe, or an eternal process, that remains beyond our current reach, tantalizingly close maybe, just beyond the fingertips. In the meantime, you're lying here in a universe that is 13.8 billion years old, give or take, made of matter that was forged in stars that exploded before our sun was born, breathing air whose atoms were assembled in the cores of ancient supernovae, resting on a planet that's spinning at 1,000 miles an hour, while orbiting a star at 67,000 miles an hour, while that star orbits the center of a galaxy at nearly 500,000 miles an hour. And the whole galaxy is moving too, carried along by the expansion of space itself, the same expansion that Hubble noticed almost a century ago, the same expansion that Lemaitre predicted, the same expansion that, when you run it backward, leads you to the most extraordinary question anyone has ever asked. How did all of this begin? Maybe it began with a singularity, a point of infinite density, where the laws of physics break down, and time itself ceases to have meaning. Maybe it began with a quantum tunneling event, the universe popping into existence from absolute nothingness. Maybe it bounced from a previous universe that collapsed before it. Maybe it bubbled out of an eternally inflating space-time that has no beginning and no end. Maybe time simply rounds off at the Big Bang, smooth and boundaryless, with no edge to fall off and no before to ask about. Or maybe the answer is something none of us has imagined yet, something so strange and beautiful that it will rewrite everything we think we know about the nature of reality. Whatever the answer turns out to be, I find it extraordinary that we can even ask the question, that beings made of stardust, living on a small, rocky planet around an unremarkable star in one of billions of galaxies, can look out at the universe and trace its history back 13.8 billion years, can detect the afterglow of its birth, can write equations that describe the curvature of space-time, and can seriously investigate whether time itself has a beginning. That's not a failure of knowledge. That's a triumph of curiosity. And maybe that's the best place to leave it tonight. Not with an answer, because the honest truth is that the answer isn't known yet, but with an appreciation for the question itself, for how rich it is, how deep it goes, how many layers it has. The question, what existed before the Big Bang, started out sounding simple. It ended up touching the nature of time, the structure of space, the foundations of quantum mechanics, the limits of general relativity, the meaning of nothing, and the very idea of what it means for something to begin. It's a question that reveals the universe to be stranger, more subtle, and more wonderful than any simple answer could capture. The universe began, somehow, or it didn't begin, because beginning requires time, and time might be part of what began. Or it's always been here, in some form or another, cycling or tunneling or inflating through configurations we don't yet have the mathematics to describe. The honest answer is that we're standing at the edge of what we know, looking out at a mystery that's as deep as any humanity has ever faced. And that's okay. It's more than okay. It's beautiful. The light from the stars you can see tonight left those stars years, or decades, or centuries ago. The cosmic microwave background that fills the sky left the primordial plasma 380,000 years after whatever happened at the beginning. And beneath all of it, woven into the fabric of space-time itself, is the question, still open, still alive, still waiting for someone to find the thread that unravels it. Maybe that someone is working right now, in a lab or at a chalkboard or on a laptop, following an equation to a place no one has been. And you, lying here tonight, are part of the same universe that asks these questions. You're made of the same atoms that were forged in the first 3 minutes after the Big Bang. The hydrogen in the water in your body was created in that primordial fireball. The carbon in your cells was built inside a star. The iron in your blood was scattered by a supernova. You are, in a very literal sense, the universe contemplating its own origin. And there's something quietly extraordinary about that. So let the question sit with you as you drift off. Don't try to solve it. Just let it be what it is. A beautiful, open, unanswered mystery. The kind that makes the universe feel vast and strange and worth paying attention to. What existed before the Big Bang? Maybe nothing. Maybe everything. Maybe the question itself will turn out to be the most interesting part. The stars are still out there. The microwave background is still whispering. And the universe is still expanding, still cooling, still carrying its 13.8 billion year history in every photon and every atom and every curved fold of space-time. Whatever came before, if there was a before, it left this, all of this. And that's enough to fall asleep to. That's enough to fill the silence with wonder. Good night.